Okay, it's time to start the session. Talking Trash by Chet, Haase, and Romain. Please give a warm welcome.
Thank you. Welcome to our talk. Let's talk about garbage. I am Chet Haase. I used to be leading the UI Toolkit team.
And I'm Romain, and I now lead the UI Toolkit team.
There's a bit of a mutiny. We won't get into the details there. So there's a common saying in computer science, garbage in, garbage out. But of course, how fast is the key? So we're going to talk about garbage allocation and garbage collection and the speed therein and the evolution of the garbage collectors on Android over time. So why? So we gave a talk last year at Google I/O, Modern Android Development, where we talked about a lot of different things, different patterns over time, what we see, the things that we used to recommend and the things that we now recommend. We basically talked on and on and on and on and on. A lot of it was about memory, recommendations about memory, such as in the old history of Dalvik, the pre-art collector that was the garbage collector and runtime up through KitKat. The collector, the runtime was optimized for size. It was supposed to be as small as possible because on the G1 and the early devices, there really wasn't much memory. So the focus of the runtime was really to be as small as possible, not necessarily as fast as possible. There were a lot of trade-offs made for that. So JIT didn't exist at first, and then when it did exist, really wasn't that fast. Allocation collection was really, really slow. So there was a lot of recommendations in early Android to avoid allocating objects pretty much at all costs. Right? And this is actually reflected through a lot of the Android APIs. If you need an object type, you're probably passing it into the method so that we don't create one on your behalf. We use ints all over the place to avoid object creation. And there was also this issue with heap fragmentation. The more objects you create, the more we have to find space for them, and the more chance you run of simply running out of space eventually because we can't actually defragment the heap over time. So this resulted in various patterns that we would then enforce, don't allocate, because then we're going to have to collect. We did sort of push people away from enums for years. That's not necessarily in the context of allocation and collection, but it's another thing that takes up memory, so just don't. And we also really liked people to use primitive types, int over integer, because A, it takes up less space, and B, it doesn't require that allocation. We can just sort of easily allocate these things on the stack.
And in Android 5.0, we introduced ART, the Android runtime, which is a replacement for Dalvik. So contrary to Dalvik, it was not optimized for size. It was optimized for performance first and foremost. So it went through a few rounds of changes. It does contain today a JIT. We also use something called ahead-of-time compilation, where we'll pre-compile the application to native code. And today on O and P, what you actually have is an interpreter, a JIT, and ahead-of-time compilation. And ART will pick one of the three, depending on what the app is doing and some analysis. ART also came with much faster allocation and collection. And this is what we're going to talk about today in the rest of the talk. We're going to explain what the ART team has done to improve allocation speed and garbage collection speed. Heap fragmentation is not an issue on ART anymore. There might be some cost depending on the version of Android you're running on. Again, we're going to talk about this in more detail. And the large object heap, which was a huge source of garbage collections with bitmaps, for instance. Many apps were running into those problems. So the recommendations that we gave in our talk, now that you have ART, is allocate when necessary. Again, Chet talks about enum. They have nothing to do with allocations, so forget about that. Use the appropriate type that makes sense for your APIs. Make your APIs as good as they need to be. Don't worry too much about this kind of optimizations. Of course, phones are still constrained. Battery is still an issue. So if you write high-performance code in an inner loop, in your drawing code, in your layout, in whatever else your application might be doing, you still might want to be a little careful. At the very least, always profile. Use the different memory profilers, CPU profiler, GPU profilers that we provide in Android Studio to make sure you know what the application is doing.
So this is what we said at Google I/O, but we said it all really, really quickly. We basically just said, take our word for it, things are better, don't worry about it too much. So what we wanted to do was look at the details a little bit more and talk about why you shouldn't worry about it too much, and how the garbage collector actually works and how it used to work and how it's evolved over time, so that you understand the trade-offs, especially if you're releasing applications for different versions of Android. So first of all, let's talk about how memory works on a computer. Let's look at some simple code here. We have an int thing, we have an int variable, and we also have an object. So we're allocating an object there, and we have this thing called the stack, and it could, and we also have registers. So we could choose, the compiler can choose, and the runtime can choose sort of where to put these things. So you have this int value, it's automatically going to go on the stack. We didn't have to allocate anything. We basically just said shove it there. It's a single instruction. It just puts it there. It's all good to go. Or we could also put it in the register. It turns out Dalvik was a register-based runtime. I think the classic JVM was stack-based runtime, but either one of these are essentially free, right? This is why we really pushed everybody to use primitive types as much as possible. On the other hand, if you have that myObject thing that's going to be allocated on the fly, we're going to have to find room for it in the heap, right? So we're going to go to this large space that we've pre-allocated in the runtime and take up a chunk of that just to hold this object. And then we get other objects in there and they take up other spaces in the heap, and then it fragments over time, et cetera, et cetera. We can take a look at how you do memory allocation in native languages, so sort of pre-Java or current C++, if you still use that, where we have this thing, we say, give us a new object, and then we write the code using that thing. And then if we never free it, well, then we've leaked it. We're taking up memory in the system, and we're never giving it back, and eventually we're going to run out if we do that stupid thing too many times. So we really need to do our own manual allocation and collection in native languages. But usually we do remember to delete that thing, and then occasionally we forget that we've deleted the thing and we use it afterwards. And that can result in a crash sometimes, right? Very non-deterministic. Basically, you really are on your own in native languages like C++. You need to manage your own memory, and it's a really hard thing to do, especially when there's multiple threads and really complex large code bases. So along comes Java and manages memory for you. Right, so we say, give us a new object, and then we write some code using that new object, and eventually that thing is freed, and there is no leak. By definition, the garbage collector does this thing for you. It will free it, and if we keep using it, if we have other code somewhere else that is still referencing that object, referring to it as well as using it, then it's not going to be freed until it actually is not being used anywhere else. It's just a magical thing. Garbage collector does it for you. However, there's overhead associated with that. So there are some questions that come up about GC. Well, if it's doing all this magical stuff for you, then at what cost? So how long does it take to actually allocate an object that is going to be managed by the runtime? How long does it take to actually free that memory back up and give it back to the heap and back to the system? And what impact does that have over the overall system? So if the garbage collector is running, is it stopping the other threads? Is it taking up CPU time that is wanted by other threads or other processes on the system? And when do these collections happen? This is a huge issue for something you've seen in your logs, especially KitKat and before, called GC for alloc. So if we're actually doing an expensive garbage collection operation on the main thread when you're trying to do something else, you will generally see a jank because of that. And then finally, how efficient is heap usage? Right? So if you have a lot of little tiny objects allocated, but the heap is fragmented, then you may be running out of memory when there's actually plenty of memory there, but just not in the right places and not contiguous. We'll see an example of that a little bit later.
So we're going to start with the garbage collector in Dalvik. So that Dalvik was the runtime we used all the way until KitKat. So let's say we want to allocate our blue object, and we need to find space in the heap. So Dalvik just walks the heap, and as soon as it finds a space that's big enough to hold the object, it just slots it there. The allocation is done. And just remember that when we talk about allocation in this part of your talk, we talk about what the runtime does for you. It's not about the constructor of your object. We're not talking about the execution of your constructor. It's really just finding a spot in memory and reserving that spot in memory. It's nothing else. All right. So then when we need to do a garbage collection, Dalvik uses a multi-step process. So you have your heap. The first step pauses the whole world. So all your threads are paused because Dalvik needs to find the root of chains of allocations, where it's the first allocation that holds on to all the other references. So here, for instance, we marked a few. Then concurrently in the second pass, we mark all the other objects that can be reached from those different routes. So your application is running in the meantime. That doesn't pause your application. Now, one of the problems that can happen here is what if your application performs an allocation while we're looking for those reachable objects? So here, for instance, a new object appears in the heap. So Dalvik has a second pass to mark those reachable objects, and this one will pause your application, but it will only look at new objects that have been created during the previous pass. So usually it will be a much shorter pass, but it has to pause your application so we don't end up doing this indefinitely. And finally, once we've marked all the reachable objects by deduction, we know which objects are not reachable, which are the objects that we can garbage collect. And so we can just get rid of them. And that collection itself is a concurrent pass. It doesn't pause your application. Now, what happens if we want to allocate an object and there's not enough room in the heap? So Dalvik's going to walk through the heap looking for a spot. There's nothing available. But we have objects that have been marked non-reachable, so we know we can collect them. And this is what's called a GC for alloc. So as we're trying to do this allocation, we will pause the application, we will pause the allocation, we'll run through all the steps that I highlighted before. So 4 steps, which will pause the application several times. We hopefully will free up some space and we'll find room to perform the allocation. Of course, sometimes, even if we do a GC for alloc, there's nothing in the heap that we can collect. And in that situation, we have 2 solutions. The first one is we can grow the heap. This is also not something you might want because it can be expensive or you will just take more RAM in the system that your application does not necessarily need. The other solution is simply to throw an out-of-memory error. And I'm sure a bunch of you have run into this issue, especially when you are allocating large objects. So either way, you don't want to run into this problem.
So we wrote a really complicated demo application to show this off. I won't show the demo itself, but we'll sort of show screenshots and describe how it works. So this application will basically allocate memory all the way up until there is no more memory. So you start off with a small heap. If you just run until that's full, that's not good enough because then the heap would grow if it really needed it. So the application basically just allocates 1 meg chunks and then keeps doing it. The heap will grow and grow and grow, and then eventually it runs out, throws an exception that we catch. So we know that we've allocated everything. So we click on this button in the middle of this fantastic UI, and we've allocated all of these 1 meg chunks up until the heap is actually full.
So in that particular case, we've allocated 400 megabytes.
Right, which you can see in that little tiny UI that is visible to nobody in the room. So now we want to defragment we want to fragment the heap. We're going to free every other chunk. So we have these, roughly 400 chunks of 1 meg blocks all the way up, and we're going to free every other one. So by definition, and as you can actually see in the UI, we have 200 megs free, right? So out of that 400 meg free, 400 meg heap, we have 200 megs free because we've freed every other one of these 1 meg blocks. So we're going to go ahead and try to allocate space for a 2 meg object. That little blue object is just 2 megabytes. We have 200 megs free, and the result is a crash dialog, right? Because even though we had 200 megs free, we didn't have 2 megs contiguous anywhere in the heap. So all we can do is crash.
And what is awesome about Dalvik is that if that happens in your application, there is nothing you can do about it. Absolutely nothing. Except try to change how and when you allocate things. So basically, you're screwed.
All right, so these are the sad and frustrating error messages that we emit. So you can see in this first one, there's a GC for alloc call, so it realizes, well, there's not enough memory, so I'm going to go ahead and do a GC for alloc. It's expensive, but it looks like, it should work. We're trying to find space for roughly 2 megs out of roughly 200 megs, and so it runs a GC for alloc, forces a collection of soft references in every attempt to do anything here. That didn't work, and then it's going to do one more sort of Hail Mary GC before it runs out of memory and try to get any memory anywhere, and it fails and it says out of memory. And I love the error message. It says you couldn't get 2 megs out of 200. It seems like Android can't do math, but it's all about fragmentation.
Yeah, and this is a problem that a lot of folks were running into in the early days of Android. A lot of bugs were filed against Bitmap Factory, saying Bitmap Factory leaks because people will run into this exact error. Bitmap Factory was not leaking. It was just a fragmented heap. And of course, Bitmap being some of the largest objects that applications typically create, those were usually where the application will fail with an out-of-memory error. So we thankfully switched to ART, Android runtime. And ART is better in every way. We have faster allocations, faster collections, and faster runtime. So we're not going to talk about the runtime, but we're going to talk about the allocations and the collections. So in ART, we introduced a new allocator called ROS alloc. I'm not sure what ROS stands for. It's a replacement for something called DL malloc. DL here stands for Doug Lee, the person who wrote that malloc algorithm. It's used on many systems. Basically, when you're in native code and you new an object in C++ or you call the malloc function in C, it runs through this dlmalloc library. So instead, it's a very generic allocator, and Art replaced it with something more specific to what we need to do. Art also introduces thread local allocations. This is a bit complicated, so we're going to talk about that in detail later. We also group smaller allocations. It's kind of related to the thread local allocations. We use a region system. Again, we're going to show an example. And we use page alignment to improve memory access. Also, one of the issues with a garbage collector or a memory system like this is that you can have multiple threads that need to allocate at the same time or to garbage collection, so you need locks. And Dalvik was using locks that were coarse-grained, so we were locking too much, and sometimes we were just staying idle when we could have been doing work. So Art fixes that with finer-grained locks. So overall, when you compare it to Dalvik, the time it takes to allocate memory is about 4 to 5 times faster than previously. All right, so here's how Art performs allocations. One of the very interesting things that Art does is it treats large objects differently. So I don't remember what the limit is. Was it 12 kilobytes?
12K. The heuristic is 12K of objects that cannot have a reference elsewhere. So it's basically primitive types and strings.
Right. And primitive types includes byte arrays, which are used by bitmaps. So let's imagine that we want to allocate a regular-sized object. So we find a spot in the heap, we just slot it in, just like Dalvik used to do. Now, if we have a larger object, we're not even going to try to find space in the heap. Instead, we're going to allocate it. So Dalvik could allocate it. We'll try to allocate it in the heap. That could lead to all the errors we talked about. But in Art, we're just going to allocate the object on a separate heap. Basically, we're just going to call malloc, and it's going to leave it in its own world somewhere else. And that way, we don't even need to grow the heap. We don't need to deal with fragmentation. So when you allocate a bitmap, it's much faster. You're not going to have a GC for alloc pause. It's also a moving collector. So that solves the problem of fragmentation eventually. So Art will try to defragment the heap to compact the heap when the application is running in the background. So you can't really control when that's going to happen. That's why we say eventually. The other situation where it will happen, and we're going to see an example for that, is when we are running out of memory in the heap. That's kind of like the last thing we can do. We've done the GC for alloc. We still don't have enough room in the heap, so we try to compact it, and maybe that will solve the problem.
All right, so let's go back to the fragmentation demo that we ran earlier. This is on all releases from L and forward. So we press the button, we allocate these 1 meg chunks. And then we press the button again, and we fragment the heap, so now every other meg is free. And then we try to allocate space for 2 megs, and it says, yep, I can do that, and it forces compaction. Now, when I originally ran this demo, I said, well, I know that it's going to work on O, because that is the first time, we'll talk about this a little bit later, that's the first time when we actually can run the defragmenter in foreground activities. Otherwise, it runs in the background when things are idle. And so I thought, well, it's not actually going to work until O, because it can only defragment in the background. But it turns out it will also force a defragmentation if it has to. So basically that GC for alloc situation it can occur on any of the releases with Art where it says, I don't have enough memory, but what if I defragment the heap? Can I fit it in?
So the trade-off is that it might be a little more expensive because we do a GC then a compaction, but also your app is not going to crash, which is a pretty nice feature to have.
All right, so that worked, and also the times got better. So if we looked at what Dalvik was doing before, we had the 2 pauses. There's the expensive first one, and then there's the shorter pause, secondary one later, where we sort of catch up on all the things that have happened in the meantime. So those 2 together take about 10 milliseconds, on some reference device in a typical load. It can take a lot longer, but this is sort of an average time in general situations. Whereas in ArtGC, that pause on the first one went away, and now that can be concurrent. We only have a pause on the second one, which is much shorter, which turns out to be about 3 milliseconds. So that it's not that the other work isn't happening, but it can happen concurrently, so we don't suffer from it when we actually need it to happen.
All right, so one of the other things that was introduced in Art is the concept of a minor garbage collection pass. So a lot of apps will allocate a lot of temporary objects. Typically within a function, you're going to allocate string builders, strings, various other small objects like this. So what Art will try to do is do a first collection for the objects that it knows have been allocated recently. So it won't try to GC the entire heap because that can take a lot of time. So it looks only at those new objects. So it's called the young generation. So yeah, temporary objects have become a lot less expensive in art. They will still trigger eventually, fragmentation or defragmentation or garbage collection, but still faster.
This is actually one of the things that triggered a lot of the patterns that we have in the APIs and early development in Android, where even a temporary small object was something we really didn't want to allocate because it was going to contribute to all the problems that we've been talking about. So we really push people to, don't do a new rect just to do a little operation inside your method. Instead, find a different way to do this. But now if we have young generation collection, everything is cheaper and faster, and you don't worry about it as much.
But just a reminder, again, it's about the allocation, so we still need to run your constructor. So if the object you create are expensive in any way in terms of computations, you still need to pay that cost. So we mentioned the large object heap. It helps a lot with fragmentation issues. We also do less heap resizing. So that's very important because we have a lot of apps running on the device. And when you resize your heap, you might not be using the entire heap inside your application. So you're safe, you're using maybe 50% of your heap, but you're still using RAM as far as the entire device is concerned. So we can run fewer applications if all the apps have a large heap. So that's very important for us. And that also led, like I mentioned, to fewer GC for alloc pauses. And again, the runtime got faster, but that's not the topic of this talk. In Marshmallow, not much, a lot of work was done in art, but nothing like, no new feature. Basically, it's a bunch of optimizations. So the team optimized the compiler, your code runs a lot faster. There's also a bunch of optimizations in the allocation code path.
One of the important things about art was that it's not just, well, it was faster for all the reasons that we're talking about today, but it was also a platform on which to build these optimizations. Dalvik, as we said, was written for the constraint of you don't have any memory at all, now go write a runtime, whereas art was written to be a modern runtime with as many optimizations as we could throw at it. So every release since it came out, we're doing these major optimizations because it was sort of built that way as a framework upon which we can layer the optimizations, as opposed to Dalvik, which kind of reached the end of the road for what it was. So we've been able to just continue building every release since then. And I think the theory is that we continue to do that as well.
So in end, we got more inlining, more optimizations. The allocator was made a lot faster by rewriting it in assembly code. So you don't have to worry about that. That was the arts team challenge. And thanks to all those optimizations in Nougat, allocations are now 10 times faster as they were in Dalvik. So again, it's not about your constructors, but allocating those small temporary objects that are cheap in terms of running the constructor is a lot faster than it was in Dalvik. Oreo added the concurrent heap compaction, so that's what Chet was talking about. The defragmentation can now happen in the foreground, so we don't need to wait until we have to do basically a GC4 alloc to run the compaction. So that results in even fewer heap resizes, even fewer GC4 alloc. And that's extremely interesting for those device-wide memory savings that I was alluding to earlier, especially because we run very important processes in the system that never get killed. So the system UI that contains the lock screen, the status bar, the nav bar, some other UI bits, and we have, of course, the Google Play services. So those things are always there, and they could take quite a huge chunk of memory because, and we don't necessarily control the allocations, especially in something like Google Play services, because the apps make requests, and depending on how the apps behave, we could be using more or less memory. So that resulted in smaller heaps for all. And here's the comparison between N and O. So N is the blue bars, and overall the heaps are about 30% smaller in O for the same applications, running with the same kind of workload. So we just save like 30% of RAM by just making those optimizations in art itself. You can also see on the right, it's the garbage collection overhead. So that's further optimizations in the code inside art that allocates things, and it got a little bit faster again.
So let's talk about how that concurrent compaction works. One of the optimizations that we had in art was to give each thread its own region to deal with. So now this is one of the reasons that we can avoid so many locks and so many coarse grain locks, is because whenever a thread needs to allocate, it can just go to its own bucket and allocate it.
And the region is a chunk of 256 kilobytes of RAM, I think.
Yep. And whenever a thread needs one, the system will just hand it another one of those from the much larger heap that it has overall. So we've got some representative view here. We have a bunch of things allocated in these different buckets. It's time to compact. So the system goes in and it looks in all the regions that have sort of sparse allocations, and it will take all those objects out of that region to completely empty it. So we can see this happen in the compaction phase. So T1 gets completely emptied, and all of those bits get shoved over somewhere else. Basically, we move the handles around in the heap. T2, we empty that out. T3, we empty that out. And now we have this concept called a thread local bump allocator. So before, if you wanted to find space for an object that you were allocating, you needed to walk the heap or keep a complicated track of where these objects were so that you could put it in the right place, right? If the thing is getting fragmented over time, you're not sure, where there's enough space to put this thing, so you walk the heap, it takes a while. With thread bump allocation, and given the compaction phase stuff that we're talking about now, we basically have the ability to just put it at wherever the pointer is. Right? So we're going to see how this works in a second. But this results in much faster allocation as of the end release, and overall an 18 times speed up since KitKat. So let's see how this works. So we have the emptied regions from before, and then we need to allocate a bunch of objects, and those get allocated over the time in these regions. If we take a zoomed in look at this T1 region, so the free pointer in the empty bucket, empty region sort of starts out at the beginning, and then an object comes in and needs to be allocated on this thread, and we simply put it at wherever the pointer was. Now the pointer is moved, we just bump it to where the rest of the free space, another object comes in, we bump the pointer, bump the pointer, bump the pointer, and all of these are incredibly cheap and fast. So the overall time speedings from all the stuff that we're talking about, you can see in the graph here, we've got basically about 18 times speed up, given everything that we're talking about, the assembly rewrite and bump pointer allocation.
And to give you an idea, in Dalvik, an allocation was about 650 nanoseconds. So it sounds really fast, but if you are allocating, thousands of small objects just because you're doing boxing of integers or concatenating strings, it's going to quickly add up to milliseconds. And that's, again, without running even your code. It was just in the allocation code path of the runtime itself. And now we're, 18 times faster, so it's basically not an issue anymore.
We're going to see a graphics demo from Romain later that will demonstrate this really well. It's a bunch of really tiny float objects, but a lot of them being allocated on every single frame, and then you can sort of see the difference in these different allocators.
So more changes in art. So we mentioned the young garbage collection that was introduced in Lollipop with the introduction of art, and it's gone in O. And one of the reasons is because, as the art team is making all those changes, all those improvements, they have to change the way the garbage collector works. It can be really complicated, and so they cannot necessarily bring back all the features fast enough. Now, the good news is that this is enabled in AOSP, and I don't know if it's in P or anyway, it might be in a future release of Android, or maybe it's in P.
That was in AOSP as of October, so
okay,
it'll be in
so not in
future release.
Right. So hopefully in the future release, it's going to be back. So it's going to get even better. We also wanted to talk about object pools. The conventional wisdom is that using objects, reusing objects is going to be, of course, faster than reallocating objects, because you're not going to run the constructor, you're not going to go through the allocation of the runtime, and you're going to have a lot of savings. So it's really hard to see the graph here. The blue line is, so the x-axis is the number of objects you're allocating.
It's the size of object.
The size of object, sorry. The y-axis is the time it takes, and the blue line is what happens when you don't reuse objects. And the red line is what happens when you use an object pool. So what you can see here is that, before O, it was pretty much always a good idea to use an object pool. There are some caveats, but basically it was faster to allocate those big objects. But that's not true anymore with all the changes that have happened in art. Because so as of Oreo, because we have this thread bump allocation, using a synchronized pool of objects will be slower than just moving that pointer, because you're going to have to acquire a lock, and that's more expensive than just doing a plus equal effectively on a native pointer. And you can see how it affects the allocation times. So the blue line, again, not using a pool, it's a lot faster than using a pool. Now, if you don't use a synchronized object pool, but use just an object pool without synchronization, it might be faster, probably not worth it, because pools of objects can be error prone. And actually, we've had a number of bugs in our own object pools inside the platform. Just the other day, PY from Square was complaining that we introduced a memory leak in P, I believe, because we added a field to an object that gets pooled, and we forgot to change the code of the pool to clear that field when the object gets reused, so activities get kept somewhere. So that's an issue. So going forward, avoid object pools unless you really, really need to use them. So profile your application and make sure that you're doing what's right for your code. So what now? That's basically what we mentioned in our talk at Google I/O that we started with. So you can create garbage. You don't have to worry so much about allocations anymore. Garbage collection is pretty much a non-issue anymore. It might still happen to depending on what your application does, you can still run into this problem, but it's going to be extremely rare. Use the types and objects you need. Make sure that you make your life easier. Make your apps easier to debug. Make your APIs easier to use. So don't use integers anymore. Well, lowercase I ints anymore if that's not what you need. But garbage collection is still an overhead. It's not free. It's not entirely free. And like I said, we still have to run the constructor of your object. So depending on the types of objects you allocate, if you're going to run, I know it sounds a little stupid, but if you run a database query inside the constructor of your object, that's going to be slow, and there's nothing we can do about that. We can try to improve the runtime, but it's still going to be a cost. So be careful, but again, not as critical as it used to be. You can free your mind a little bit and think about other problems that you have in your application. I'm sure you have many that you have to deal with. So just make the right choices again for what you're doing. One of the places where you still need to be careful is critical sections. So anything like touch event handling, drawing code, rendering code if you're using OpenGL, for instance, layout, measure, that kind of stuff. The kind of code that gets called all the time. And that's why on the platform, we are still pretty careful about this, because our code tends to be in the hot loops of the applications. But there are other places where we don't care. Like, in the click handler of a button, it doesn't matter if you're allocating something.
All right, so now let's take a look at a demo. The original idea for this talk was, well, we talked about all these GC concerns and patterns and modern advice, but let's just demonstrate it through code and demos. And it turns out that's a really hard problem. Garbage collector is running asynchronously, and if you want to trigger a specific thing to happen at a specific time and for it to have specific behavior, it won't be possible. I know, I tried really hard. So you can demonstrate some sort of coarse-grained stuff like the fragmentation stuff before, and I'll show some jank test stuff here to sort of show you what the overall overhead can be, but it's really hard to write a deterministic demo. I just want to say that as my excuse. All right, so we have some simple code in this amazing demo I'm about to show you. Every time through the draw loop, we then call out to a routine that's going to do some auto boxing. It's going to force some auto boxing. So we have this float array, capital F, size 100,000, and then again, on every frame, we're going to call this run method, and we're going to say, okay, for each one of these float objects, we're going to stuff it into the array, and it's going to auto box on the way, right? Because we have a primitive type, and we have an object array, so it's going to convert it to the capital F float, which means it's going to ask for this little tiny bit of garbage on the heap as we go. And then what happens? So let me switch to demo and see if I can drive this remotely. This is going to be fun. I want to go to this. That is the O version. This is the KitKat version. All right. So here's our demo. We have All right. I would show you I should have had another option in here to show the non-auto boxing version.
I told you many times.
Yep. Okay, so instead, I'm going to show you what happens. So this is running through the code that I was showing you. There's a green square that's being animated on the screen. It moves a little bit for every frame. And every time you see it flash to red, that's because we janked at least one frame. So we're timing the interval in between each frame, and it should be roughly 16 milliseconds. And every time it's more like 32 or more, then we turn it red because we've just missed a frame due to whatever is going on in there. What's even more interesting is what you can actually see in the log here. I'll need to zoom in. So you can see all these. Let's go down to the bottom. So hard to see. Yeah, GC for alloc, taking pause for 6 milliseconds. The allocation time itself was taking 28 milliseconds. And then there's about 38 milliseconds in between frames. And that's sort of a general average here. Basically, we're just forcing so much garbage on the heap, then every time through the next time through that loop, then we need to do a GC for alloc just to free up the memory there so that we have enough to keep going. And then we just end up in that constant janking state. Let me pause this guy and come over here and show you on O, we've got auto boxing. Change the log over to, oh man, is this difficult? All right. So this is the log for the O emulator. We'll run the animation, and then we see there's an occasional jank. Sorry, the green line down at the bottom is sort of 16 milliseconds, and this is the actual frame time, the little flicker that you see there. There's an occasional red, but not really much. And now if we zoom in on the log here, we can see basically no GC for Alex and allocation times of sort of 2, 3, 5, 6 in general, right? Because things are just faster and we're concurrently collecting. We never get into the state where we have to throw up our hands and say, okay, time for a GC for Alex, because there's always enough space to keep going. All right. These basically just back up the stuff that we just saw. Okay, so then the other side of it is bitmap. So due to the large object heap, it's much faster to allocate space for these really large objects. Not only that, but it's much easier to then deal with the rest of the heap because that's just small objects there. So again, wrote a little bit of code that runs every time through the draw loop and then time what happens, time the interval between these frames. And we're just creating a bitmap, a single bitmap each time. It's 1,000 by 1,000. So it's guaranteed to hit the large object heap as of the art collectors. And then we can take a look at these demos again. So here's K. Let's see the log. Change this to bitmaps, run the animation. And it's not as bad as the autoboxing test. We're just allocating this one single object, but it occasionally janks. And more importantly, if we take a look at the log, you see all these GC for Alex again. Pause 6 milliseconds, allocation time 14. So it's sort of running right up to that frame boundary. But man, if you're taking 6 milliseconds out of a 16 millisecond frame boundary, then chances are the rest of the stuff going on in your application is going to cause jank. Very commonly on the UI thread, and then that is going to be disruptive to the user. Meanwhile, if we switch to the O demo, I like the awkward pause in the room while I do this. If somebody knows this song, actually don't. All right, let's switch to bitmaps, run the animation over here. That was one jank, so there's an occasional jank there, but much better in general. You see the times over here, sort of allocation time commonly of 0 to 1, because all it's doing is a malloc. It says, yep, I can put that big object right down there. That's it.
So here's another example. That was for a talk I gave at Kotlin Conf that initially was not about Android. And I wrote this little ray tracer demo. And I used a lot of fancy features of Kotlin. So how many of you are familiar with Kotlin already? Okay, so for those of you who are not, so I created a data class. It's called float3. It's basically a vector. It has an X, Y, and Z float. So it says capital float, but in Kotlin, that doesn't mean that it's an object. In this case, those are primitive types. So I just have a class that holds, 3 lowercase floats. And here there's a function, it's just a representative of the kind of code that the ray tracer runs on every frame. So just a bunch of math. And Kotlin lets you override operators. So if you look at the bottom, it says, x times a times x plus b divided. And every one of those operators run through a function that looks like this. So for instance, the plus operator creates a new float3 object every time it's invoked. So, it makes the code a lot easier to read, a lot nicer to write, but it's creating a lot of objects. So same thing for multiplication, division. And, to render a frame, so we have thousands and thousands of pixels, and for each one of those pixels, we have to run thousands and thousands of multiplications and additions and divisions. So we're creating a lot of objects. So here, I have 2 emulators. At the bottom, you have KitKat. At the top, you have O. They're both emulating a Nexus 5X. They're running on the same host machine. So it's a MacBook Pro from 2016. It's running at the same frequency. So everything is pretty much equal. The only difference is the garbage collector. And you're going to see that the ray tracer uses multiple threads to render the image in tiles. So you're going to see like small tiles appear one after the other. And when I'm going to click the key on the laptop, I'm going to run both demos at the same time, and you'll see how faster O goes compared to K. So again, O is at the top, right? So pay attention. It can be
very subtle.
Very subtle.
Wait for it.
So it will actually take 45 seconds for K to render the first tile at the bottom.
Oh, but it's totally worth it.
It's totally worth it. And the only difference is garbage collection, nothing else. So I can try to move the time a little bit. Where's my cursor? I'm going to show you that I'm not lying. It's actually working. Here we go. One
Nice.
tile, see? All right. So on O, computing one tile takes between 0.1 to 0.5 seconds. It's doing a lot of computations. And on K, it takes 40 to 50 seconds. So we have 2 orders of magnitude. O is 2 orders of magnitude faster than KitKat, just thanks to the garbage collector. Just for kicks, this is a log of a few seconds of KitKat trying to render that scene. And it's just GC for allocs all the time. All the time. I think that's 10 seconds worth of logs. So the poor KitKat is basically not doing any computational work. It's just waiting for the GC to be done.
That was all within one frame. That was a few seconds, but just part
Right.
of a frame. Yeah.
All right. But, even with all these improvements in O, things are not exactly perfect. So here I have systrace, and it's going to be really hard to hold my mic and show you at the same time. So these are the threads of the application. So here you see 3 threads. Those are the threads that are actually rendering the image. And there's those little blocks here, for instance, the thread blocks. They may be hard to see, but there's no need in zooming on them, during which we're not doing any computation. So, O is supposed to be really fast. It's supposed to be this fantastic concurrent garbage collector. And yet sometimes we are not using the CPU to do computation. And the reason is because we have this thread here, and that's the garbage collector. Because my demo is creating so much garbage that every garbage collection that happens in the background takes, let's see if I click on this, it says, it's hard to read. I've seen it takes 15 to 100 milliseconds. So we're using an entire core on the device just to constantly collect garbage. And from time to time, because the garbage collection is not quite finished, Art will still have to grab a lock, waiting for the previous garbage collection to be over, and that's when our threads are going to pause. So even though O is extremely good, it's very efficient, it's awesome, you still want to be a little careful if you do something as computationally heavy as the example I just showed you. But most of your apps will never do this. So just be aware of it, don't worry too much about it. And to finish this talk, the last thing I want to mention was one of the problems with garbage collection is that it can greatly affect benchmarks. So if you ever write benchmarks for your application and you're not careful about how you write the benchmark, you might get numbers that are way, way better than what will actually happen in the real world in your application when it's running. So we're going to take a step back and talk about CPUs and how they work. So I took the example of the Pixel 3. So the Pixel 3 has 8 cores. It has 2 sets of cores. There's the gold cores and the silver cores. And I'm just going to take the gold cores as the example. So the gold cores are the more powerful cores, typically the ones that are used when your application is in the foreground, running animations or drawing. So we have 4 cores. Each of those cores contains a cache called the L1. So each one of those caches is 64 kilobytes of memory. And the cache is organized in what's called cache lines. The cache line is 64 bytes of RAM. Then each core also has a cache called the L2, and those are bigger. They are 256 kilobytes. And finally, there's one cache called the L3 that's shared by all the cores, and this one is 2 megabytes. And knowing about those caches is important. So here's an example. We have a float array, just primitive types. It's Kotlin code, so no objects here. And when we access the first item of the float array to store it in a variable called A, what the CPU is going to do is going to look for that data inside the L1 cache. The L1 cache is very tiny. It's inside the core, so the access times are really short. It's in the order of just a few nanoseconds. If it cannot find the data in the L1, it has to fall back to the L2. The L2 is a little bigger. We can cache more data, but the access times are slower. It's going to be in the order of like 10, 20 nanoseconds, something like that. Again, if we can't find it, we have to go to the L3 cache, much bigger cache, even slower to access. If it's not in the L3, we're going to go to RAM. And to write a performant application, obviously, you don't want to fall back through all those caches because it's going to slow down the application. All right, so let's take a more complicated example. So it's a little hard to read, but I've created a list of arrays. So we have n arrays. Each one of those arrays is 4 floats, and 4 floats is what? 4 bytes per float, 4 times 4 is 16 bytes. And if I write a loop and allocate, so each array is represented by a small short red bar, And if I allocate all those arrays one after the other in a loop, they will all be allocated in RAM next to each other. And you can see I've represented a RAM with a width of 64 bytes, and that's going to be important in a little bit. So we have all those arrays that are neatly next to each other in memory. And then I wrote, a very simple benchmark. It's a loop. I just go through the list of arrays, and then access one array after the other. So here I have a variable called A. I access the first array in my list. And what's going to happen is, sorry, let me go back. Because it's not in the L1 cache, the CPU will go fetch the data that basically the content of the array. But the CPU never fetches exactly the amount of data you're asking for. It always fetches a cache line, so 64 bytes. But because all our arrays were allocating neatly next to each other in memory, it's going to fetch the first array and the next 3 arrays at the same time. So now I have 4 arrays worth of data already in the cache. So when I try to access the second array, we don't need to go back to RAM or the L2 or the L3. It's already there. So basically, it's extremely cheap. And same thing for the third one and the fourth one. Now, if I change the demo, and instead of allocating all the arrays next to each other, I allocate some garbage between the arrays. I basically space them out enough that they are spaced by more than a cache line. So what happens is that when we run that same loop, when I access the first array, the CPU is going to grab the data. It's also going to grab a bunch of garbage that I don't care about. So then when I want to grab the second array, it has to go back and fetch data again. So suddenly, we're spending 20 nanoseconds, 40 nanoseconds, 100 nanoseconds, whatever time it takes to go through the different caches to go fetch the data we need. So already, we're running the same code. We're running the same algorithm. The only thing I change is where the data is in memory. And now the same loop is running basically 3 or 4 times slower than before. And to give you an idea, so I run numbers on the Pixel 3. If I allocate everything in memory properly, I've normalized the values. It's the first bar, so it takes, let's say 1 second. Then if I thrash the L1 cache, so if I space the arrays so that they don't fit neatly in the L1 like I just showed you, the code runs takes about twice as much time to run. Same algorithm, same device, same CPU, same everything. Now it's twice as slow. And if I allocate even more memory between the arrays to make sure that the data is not in the L2 cache, now the code is running over 5 times slower. Again, same CPU, same everything, right? So one of the problems is that when you're doing benchmarking, you are probably going to create the ideal case for the memory access. And that is never what's going to happen in your application. And part of it is because we have those regions, we have the compaction, we have the garbage collection. All those things will move the memory around and will completely change the access patterns. And on modern devices, one of the killers for performance is the memory access in the caches. So,
sorry, I was just going to say, so when we were talking about the compaction, remember the diagrams with the different regions before? Imagine you've allocated all these things together, and then at some point the heap compacts, which means it grabs those things that you nicely allocated next to each other and puts them next to a bunch of memory allocated by some other thread, right? Or just moves them around in memory randomly, which means that's going to affect the performance because of some of these cache concerns. So
depending on what you're trying to measure, if you're trying to benchmark the algorithm itself, you probably want the memory access patterns to be perfect. So you want all the data to be next to each other, contiguous in memory. But if you're trying to benchmark the real world performance of your application, you might want to do what I did in this demo, which is between allocations, allocate some random stuff just to make sure things are moved around in memory or force a few GCs. It can be difficult. So again, use the profilers. We have systrace, we have the memory profiler, we have the sampling profiler. They're all in Android Studio, and that's the only thing you can do to make sure that your application is running properly. And we are out of time. I think we have time for maybe 1 or 2 questions.
I think we have time. We have 5 minutes? 5 to 10? Yeah.
Okay.
1 minute.
We can take 1 question, or we'll be at the office hours on the show floor. No question? They just want to get out of you there.
Apparently.
All right.
Okay.
Well, thank you very much.
Thanks.